Hi, everyone. This is the Hungry Math Professor here, and today I'm going to be discussing this book, Philosophy of Mathematics by Oystein Linnebo. This is a very good book on the philosophy of mathematics. You could think of it as like an intro textbook you could use for a philosophy of mathematics course. And I think it's very readable, though I put an asterisk on that in the sense that if you have no background in mathematics or philosophy, then this is not going to be readable for you. I think that's important to note. But if you were if you were a math major or a philosophy major at some point, and you want to get back into it, or you're in mathematics or philosophy and you've never tackled philosophy of mathematics, then I think this is a good book for you. But I think you do need some exposure to logic and symbolic languages and just mathematical thinking or philosophical thinking in order to be able to tackle this book. But if you do have that background, then this is a great book for you. And in particular, there's lots of different books on philosophy of mathematics. A lot of them I will do discussions of on this channel. This one focuses on mostly the development of foundations of math and philosophy of math in the 19th and 20th century, which is a very exciting time in the philosophy of math and in foundations of math. In particular, one thing that I think is distinctive of this time period um, is that the philosophers, the logicians and mathematical logicians, and the mathematicians are cross-pollinating much more than they do now. In some sense, there's not really even a clean distinction sometimes between any individual and where they fall in those three categories. And if there is a clean distinction, they are still very much cross-pollinating with each other. And so that makes a very exciting time. And I think that's very healthy for the discussions that come up in the foundations of math in this period. Whereas today we tend to be completely separated. Pure mathematicians are separated in most part from mathematical logicians and are very much separated from philosophers. And there's very little cross pollination between these groups. And I'm not so sure that that is good for the kinds of questions we want to ask about philosophy of mathematics and foundations of mathematics. But anyway, so Lenovo starts off by he has to pick some part in history to start with, right? And so a very natural thing he does is to start with Kant's philosophy of mathematics. And in particular, he uses Kant's distinction between analytic and synthetic ideas and the sort of important distinction between a priori and a posteriori ideas, which is very important to modern philosophy in general. And he uses this to build a table and of where philosophers can fall on these two distinctions. And he uses that to just organize some of the people that are going to come up in the rest of the book. So I won't explain these distinctions here. I'll let you look them up because there's good explanations online and they're kind of things you need to really mull over and hard to just kind of watch me talk about. But it's a good place for him to start just by introducing Kant's philosophy of mathematics. He's not going to spend much time there. And some of these distinctions is just a way for him to start the book off. But then in the next chapter, he jumps into Frege's logicism. And Frege is really important because he develops, Aristotle is famous for starting the discussion of logic, but it takes until Frege to really develop that into what we think of now as this sort of first order logic with the quantifiers and things like that, which is the basics of mathematics and foundations of mathematics, set theory and philosophy. Like this comes up all over the place. And Frege was a big part in developing that, but he also had this philosophical interest in trying in logicism, which is this idea that if you want to say, you know, what is mathematics? What is mathematics about? How do I give a foundation to mathematics? For Frege, the answer is to ground all of mathematics in logic, right? And logic is often seen like the axioms of logic are often seen as self-evident. Um, we can debate that, but I think there's a lot of us who believe that the rules of logic are fairly self-evident. And so if all of mathematics can be boiled down to logic, then that would mean that sort of all of mathematics is self-evident, just like logic is. And we would just need to accept some very, very basic facts about logic, and then all of mathematics would follow. You can see how that's a pretty big deal and a pretty big project. And it turns out that as Frege was developing all this, there was a big problem noticed by Bertrand Russell, which is Russell's paradox, and it was like a nail in the coffin in a lot of ways to what Frege was doing. But that being said, Frege's influence on mathematics is still huge because of how he developed, quantification logic, which is such a big part of everything we do today. But then this sort of project of logicism was taken up by Bertrand Russell and Alfred North Whitehead, and they wrote these three massive volumes called the Principia Mathematica, and that came out in 1910, 1912, and 1913. I mean, they're just these massive books that are extremely technical, and they're trying to fix, Russell's paradox, which was a paradox which put an issue into Frege's approach. But they were trying again to reduce all of mathematics down to logic. And this is largely seen as, or completely seen as, a failure at this point. But again, it's hard to overstate just because the overall project was a failure. The development has so many impacts on, the mathematicians and philosophers and logicians at the time, and has had a lasting impact on the field. But this sort of big logicist project of the time is certainly seen as a failure, but there are other ways perhaps of being a logicist now. And then so this is a good place for them to start. And then it goes into formalism and Hilbert's program. I've discussed quite a bit of Hilbert's program in other videos, so I won't go back into that again. And just kind of going through the chapters and commenting on them. The next chapter is on intuitionism of Brouwer, and this is a approach in the philosophy of mathematics that is largely been um, lost to, I think, mathematicians. For the most part, we're not really aware or so interested in this. But Brouwer was really trying to be quite conservative about how we develop mathematics. He was very skeptical of some of the logic in proofs by contradiction, and he was very much a big proponent of, constructivist kind of theories that you need to be able to construct um, any of the things that come up in your mathematical arguments. And so he represents a very conservative view towards mathematics. And that conservatism, I think, is grounded in the idea that we want to make sure that what we're proving in mathematics is really true and is justified right down to the foundation. And so he was he represented sort of a he wanted to limit some of the rules of logic that mathematicians could use. The interesting thing, though, is that there's always this trade-off in, when, as a practicing mathematician, you don't want to be too conservative because you want to prove theorems. And I think Brouwer's philosophy was quite unattractive, in part because of how limiting it is to what we can prove, right? And so it's been lost in a lot of ways to and the mathematical community does not really discuss this at all, but it's an important part of the history of the philosophy of mathematics. Then from there, he moves on to empiricism about mathematics, and here he focuses on Mill and Quine. And I won't get into too much of that detail here, but I did want to focus on the what's called the indispensability argument. And this argument is put forth by Quine and also attributed to Putnam. And I'll just read the premises for you, or I'll give you the idea that so existential quantifiers incur ontological commitment. That is, for a statement of the form, there exists X such that phi of X to be true, there must be some object that satisfies the condition phi. When we make existential statements in mathematics all the time, we're claiming that something exists. And the next premise, natural science makes indispensable use of theories that quantify over abstract mathematical objects. Certainly, all the science that I've ever learned uses mathematics as a tool to explain what science is trying to say. Premise three, we have reason to believe what natural science tells us. And then the conclusion is we have reason to believe that there are abstract mathematical objects, right? So this argument is trying to argue that we should believe in the existence of mathematical objects, this is a big debate in the philosophy of mathematics. Like, are mathematical objects real in some sense as abstract things, or are they just sort of, you know, just products of language or something like this, sort of useful formalisms or something? So, when you have a argument like this in philosophy, you can ask whether the conclusion follows from the premises. I think in this case, the conclusion does follow from the premises. The question is whether you accept these three premises or not. And I think that's where we can really argue and debate. Personally, I'm not so convinced by this argument, but even an argument that I'm not convinced by can sharpen up good questions in my mind and can kind of focus me in on what I should think about. And so I still think this is like an argument worth thinking about, even if only to just disagree with it, right? Because again, it sharpens up our understanding of these things. And so this is a famous argument for the existence of mathematical objects. And the reason why that's interesting is because the next chapter that Linnebo goes into is nominalism, which is a area in the philosophy of mathematics which says that mathematical objects do not exist, and then tries to defend how that could be possible. Again, if you think that mathematical objects do not exist, the tricky part for you now is to explain why is there so much consensus about mathematics? Why do we seem to agree? And why should we think then mathematics is certain in any sense, or where does the legitimacy of this field come from if there aren't these sort of mathematical objects? But one thing I want to sort of highlight in the nominalism chapter, which I find really interesting, is that the work of Hartree Field, where as a way of sort of disagreeing with one of the premises in this indispensability argument, which is that natural science makes indispensable use of theories that quantify over abstract mathematical objects. Well, you could say, yeah, that's true, that all of science definitely right now uses mathematical objects to describe. Perhaps that's just a matter of convenience. Perhaps it's just really difficult to communicate science without mathematics, but not impossible. And so what Hartree Field attempts to do is to show that all of science can be ridden of, you can remove all the talk of abstract mathematical objects completely. And he's trying to show that all of science can be done by just referring to the physical world. And hence he's trying to show that the use of mathematics is simply a useful one, it's a practical one, but it's not a necessary one. And if that's the case, then he makes up a lot of ground in showing that the indispensability argument, that one of the premises doesn't make sense. Now, this is a very difficult project. I think he's probably successful in some ways, but certainly we have not seen all of science change to this approach. And again, he's not trying to necessarily change practical science, but I think it's largely seen that this was a very difficult project and probably unsuccessful in the whole, that mathematics does, or science does, need to use mathematics in some way. But I think it's an interesting approach to think about whether we really need essentially to use mathematics to describe science, or whether it's just a very useful and a very good idea to do that. In any case, the next couple of chapters I want to just kind of highlight is there's one on mathematical intuition. And here, I think that, we use the word intuition in the classroom. I use the word in the classroom all the time. There, I'm just really using the word to talk about, experience with mathematical objects. How many exercises have you done? How many examples have you looked at? So I'm using the word to just kind of, in a practical way, in a pedagogical way, to say that if you've never studied, the sizes of infinite sets, then you have no intuition for that subject. But the more examples you look at, the more exercises you do, the more you build up your intuition. Here, I'm just using intuition though as like a stand-in for experience, perhaps, right? Or how much have you thought about something? But in philosophy, this word intuition gets used in lots of different ways, and it gets quite thorny to try to give a precise definition of what that means. You can use this intuition as some sort of access we have to mathematical objects, perhaps, right? And again, I'm not going to try to defend that, but I just want to give you a sense of how this word gets used in the philosophy literature. There's a section on that. There's a section on, there's a chapter on abstraction reconsidered. Again, abstraction is a very important part of mathematics. When you look out in the world, you never see mathematical triangles, right? You see things in the world that where triangles could be useful, but you don't see these perfect triangles. You don't see any lines anywhere, these sort of one-dimensional lines or these points. You don't see any of these objects in the physical world as far as we can tell. And again, it's not that we can't use these things to talk about the physical world. We do that all the time. But the important part to realize here is we never actually see physical objects, mathematical objects in the physical world. And so that's the abstraction of mathematics, right? When we talk about the number four, we tend to explain this to kids by abstracting away groups of four things. But none of those groups of four things is the number four, right? We're abstracting away from all these groupings of four things, the number four. And anyway, that's such an interesting part of the philosophy of mathematics. Like, what is really going on when we do that, and what grounds this abstraction? Um, and then the last couple of chapters, there's one on the iterative conception of sets. Remember now, Zermelo-Fraenkel's set theory is the default foundation of mathematics. And for the most part, mathematicians don't really even go there and think about it very much. But if you want to start thinking about why should sets be the default, one thing to think of in the philosophy of set theory is this sort of iterative conception of sets. And he goes into the axioms of set theory and discusses those, which is really interesting if you're wanting to think about why set theory is a good foundation or is not a good foundation. Then there's a chapter on structuralism. And for any of the mathematicians out there who may be listening to this, I would encourage you to look up structuralism, because I think in a lot of ways, when a modern mathematician reads about structuralism, it feels like the modern orthodoxy of what mathematicians just already think. Most of us mathematicians do not spend much time thinking about the philosophy of our subject. Um, in my experience. But I think if you look at structuralism, you'll realize that perhaps this is just the default philosophy that we've just been trained in, and it feels very comfortable to read about. And it's sort of like preaching to the choir. But the reason why I would encourage you to read about it, because you'll also see some of the issues with structuralism. And it's interesting to kind of dig in a little bit and see what's going on there. But the point of structuralism is just that when we talk about a mathematical object, we're not talking about any particular expression of the natural numbers, for instance. Instead, we're talking about like all those structures which satisfy a certain axioms which describe the natural numbers, for instance, right? And that's the point of view of structuralism. And then the goal is to then show that like whatever structure you're talking about, like let's take the real numbers, for instance, as a complete ordered field. Then the goal of structuralism is to show that there is only one complete ordered field up to isomorphism. And then that is what the real numbers are. It's just the equivalence class of all these structures up to isomorphism. So that's what structuralism tries to do, is to say that's what mathematical objects are, just sort of this equivalence class of structures. And then the last chapter is on the quest for new axioms. So at this point in our understanding of ZFC, we know that the continuum hypothesis, for instance, is independent of the axioms of ZFC set theory. And so, but the continuum hypothesis, I think, is a very natural question about the real numbers. I've mentioned it before in another video, but I'll just bring it up one more time to end this video. We know that the natural numbers are a different size of infinity than the real numbers, for instance. And so there's a question of whether there are any subsets of the real numbers who are infinite and whose size is strictly between the size of the natural numbers and the size of the real numbers. And that's one way of phrasing the continuum hypothesis. And we know that it's not just that we haven't yet answered this question, it's that we know that you cannot answer this question using only, the axioms of Zermelo-Fraenkel's set theory. So in this last chapter, Linnebo tries to explain how some people have dealt with this. Some people have argued that we need to add another axiom, and that sort of tells us the answer to the continuum hypothesis, and that gets into lots of thorny and interesting philosophical questions. Another person's approach to this, which is Joel David Hampkins, which I've done a video on, his approach is to say that there are just many different universes of sets, this sort of multiverse set theory approach, and there is no one answer to the continuum hypothesis, but rather it depends on which universe of set theory you're in, which answer you'll get. And so again, my approach here is not to answer this question for you, but rather just to introduce it to you as a very interesting question that I think is still important to set theorists, is still debated at the foundations of mathematics. And again, I'll end the video there. This is a very good book. I hope you check it out. Let me know what you think, and like, comment, and subscribe. And I hope to see you at another discussion.